Hi, welcome to this lesson on number patterns arithmetic series. So what is an arithmetic series? Well, first of all, let's start with its definition. A finite arithmetic series is the sum of the numbers that follow an arithmetic sequence. So recall that an arithmetic sequence is defined by this general formula where the nth term of the sequence is defined as the first term of the sequence A, right? So the first term is A, plus n minus 1 times the constant difference d. Okay, where n is a natural number. So for example, if I let Tn be the sequence 1 plus, and we'll let d equals 2 times n minus 1, then if we distribute that out, we'll have 2n minus 2 plus that 1, so we'll have 2n minus 1 for natural numbers n. So if I plug in natural numbers, so from 1 onwards, we'll see that we'll get the sequence 1, 3, 5, 7, 9, 11, and so on. Okay, so these generate all the odd natural numbers. This is an arithmetic sequence where to get to the next term, you're adding a constant difference of 2. So the arithmetic series, mathematically speaking, is the sum of the first n terms, and we denote it by this terminology here, S sub n. So for example, in this sequence here, Tn, the sum of the first term is just the first term, 1. The sum of the first two terms, S2, is 1 plus 3, which is 4. The sum of the first three terms is 1 plus 3 plus 5. So that gives you 9. Okay, so that is how we can denote the sum up to the first n terms of an arithmetic series, which is generated from an arithmetic sequence. Okay, but before we get to how we define these formulae for these arithmetic series, there's a nice story that mathematicians have passed on how a very famous mathematician was actually able to generate a very nice logical way of counting numbers in an arithmetic sequence. Okay, so I just want to backtrack and quickly say that when I spoke here, I said the word finite arithmetic series. So why did I say that? Well, if I looked at an infinite arithmetic series, that would be the other case. Those are quite boring because if you add up numbers in an arithmetic sequence, like for example here, and you tend towards infinity, you're just going to get larger and larger numbers, and essentially the sum will diverge off to infinity or negative infinity, depending on what the sequence looks like. Okay, so that's why we generally look at finite when it comes to arithmetic series. Okay, so this mathematician here, German-born mathematician Carl Friedrich Gauss, in the 1700s, when he was around 6 or 7 years old in primary school, back in his day, calculators weren't a real thing as yet. So to keep a very busy class that was quite loud and noisy, a teacher would give the class a problem to try out. So the problem was as follows. The teacher assigned to the whole class and said, I want you to add up the numbers 1 plus 2 plus 3 all the way up to 100, and I want the answer. Okay, so these were only 6 or 7 year olds, so the teacher would assume, okay, this would take the students quite a long time to work out. But not for Gauss. Gauss had a bit of a brilliant mind, and the way he thought about things was really genius when it came to what we now consider arithmetic series. So he said, well, that might probably just take too long to count. So I'm just going to call this number S100 or Sn. Okay, so the sum of the first 100 terms. Now I'm going to count it another way, Gauss said to himself. So he said, I'm going to count it backwards. I'm going to count it as 100 plus 99 plus 98 plus all the way up to 1. Now that number is still S100. That's sum of the first 100 terms. Notice that this is a arithmetic sequence as well. The first term is 1, and the constant difference is 1 as well, because you're just adding 1 to get to the next term. So what Gauss did, and what was really brilliant, is that he said, well, I'm going to group these terms now. So 1 plus 100, that's 101. 99 plus 2, that's 101. 93 or 98 plus 3 is 101. so on, all the way up to the last terms here. 100 plus 1 is 101. Okay? So he added those, but he knew that the first sum was also equal to S100 and the second sum was also equal to S100. So there were two amounts of that S100 that we've just added together. But now, how many 101s did Gauss have? So he counts 1, 2, 3, all the way up to 100. So there were 100 amounts of 101. So mathematically, that just meant that if you add a number repeatedly, that is multiplication. So there were 101 amounts of 100. And that must equal 2 times the sum that we were looking for. And simply to get that sum, we divided both sides by 2 to get rid of that 2. So therefore, Gauss quickly found that the sum of the first 100 terms, 1 plus 2 plus 3 all the way up to 100, was simply 101 times 100 divided by 2. Now this was a far simpler calculation to do, rather than the tedious adding up the numbers one after the other. So 100 divided by 2 is 50, and we have 50 times 101, which was 5,050. Gauss's teacher was so stunned that he was able to come up with this formula in a matter of minutes. And it took the teacher quite a bit of time to go and count all the numbers manually to check if Gauss was correct, and he was. Okay, so that's a really cool backstory of how arithmetic series and the formulae, how we think about it today, was derived all the way back then. All right, so an arithmetic series is a sum of an arithmetic sequence. Okay, so this is just to reiterate what Gauss did. Like I said, if we call that sum S, and we write it out exactly the same way, but backwards, so 100 plus 99 plus 98 all the way up to 1. And if we add both sides, we have 100 amounts of 101. Okay, so that is what an arithmetic series is. It essentially is looking at an arithmetic sequence and then adding up the terms in an arithmetic sequence. Awesome. I'll see you in the next one.